Welcome, ladies and gentlemen, to 8.2. This is part 1 of 2 dealing with torque. So you've maybe heard the term torque before. I got a couple pictures. Maybe you've heard of a torque wrench. Maybe you've heard TV commercials where they talk about trucks having lots of torque. What torque is the ability for a force to turn something. So we're going to talk about torque, how it relates to different physics problems. So the first picture here is there's two hands on a wrench, and there's hand A and there's hand B, and hand A is 1 feet away and hand B is 2 feet away, and hand A pulls with a force of 20 pounds and hand B is pulling for the force of 10 pounds, and they have the exact same amount of torque. We'll figure out exactly what torque is here in just a second. So the actual definition of torque is the ability of a force to turn an object. The ability of a force to turn an object. So we've all maybe opened a door at some point in time in our lives, and we've all maybe embarrassed ourselves by trying to push on the wrong side of a door, and you've experienced torque firsthand. You've got a door that's being pulled on at 6 different locations at 6 different angles, and some of them are really good at opening the door, and some of them are really bad. For instance, if you exert a force on the hinges, there is no turning effect. If you push in the middle of the door, that works pretty good, but the maximum effect is when you push on the very outside edge of a door. Same with now the angle. Let's say you push at the doorknob. If you pull directly away from the hinge, there's no turning effect. If you pull at 45 degrees, there's a little bit of effect. And if you pull at a right angle to the door frame itself, then you have maximum effect. So some forces are really good at turning an object. Some forces are not really good at turning an object. So here's how I define torque. Like, we use the Greek letter tau. It's like a backwards J, and it's force times distance. Now, it's not just any force, because you'll note that in all these cases, they use the same force, and it's the same distance away from the hinges. But some of them had lots of torque, some of them had no, but it's specifically the force perpendicular. The force perpendicular, so you go back to these right here, there is no perpendicular component to this guy right here. So in this one, you've got a parallel component and you've got a perpendicular component, and this is the guy right here that you're going to plug in to this equation when you're doing this one. And then this one, this is all perpendicular. So in this case, since it's the whole force itself is perpendicular, you're going to plug that guy into the equation. So we're still going to be stuck using sines and cosines. So for instance, here's my a wrench that I've got, and I've got a force that's pushing on this wrench. What you're going to have to do, we call this the force parallel, and we'll call this the force perpendicular. This is the guy. And then this distance right here, we call it the lever arm. It stands for D. D is the lever arm. So in this case, we'll put R in that, and you can find the torque of this guy right here. Your book will define torque as FR sine theta. I don't like to use it because you have to always remember to use this angle right here. Because if you'll notice in the problem that I put out, maybe I give you this angle, and a lot of people will mistakenly throw that in there when in fact you have to always use the angle with respect to the lever arm. I don't like to get into the habit of doing any of this, so I just throw this whole equation out, and I just understand that I have to make sure I use the force perpendicular. So that way, if I give you either angle, you can logic your way through it. Like if this was 60 degrees, you could most definitely know that's 30. Or you could set your triangle up like this and utilize that 60 degree So I feel like my way is a little bit more versatile when it comes to finding the perpendicular force. So let's try a couple of example problems. The first example says there's a bolt on an engine car that needs to be tightened to a torque of 35 Newton meters. These are the units of torque. It's force times distance. You have to make sure that you put the dot in there because otherwise that says nanometers. You got to put the dot. It's important that you keep the dot in there. You use a 25 centimeter long wrench to pull off the wrench at an angle of 60 degrees from the perpendicular. How long is the lever arm? So here's your wrench. I make wrenches. I start with a house. I make like a thing around it, and here's my right there. So here's the perpendicular to the wrench, and you're pushing at 60 degrees to that. And you pull actually. So I think what I'll do is I'll just flip this around. I'll make sure that I pull on it with the force of that. You need a torque. So here's my equation. Torque is equal to the force perpendicular times the distance. The torque you need is 35 Newton meters. So here's 35. The wrench is 25 centimeters long, so this distance from here to here is 0.25 meters. It's my distance. So how long is the lever arm? Maybe I'm being just crazy, but I think it's 25 centimeters long. That's really ridiculous. I don't know why they'd ask you that. And how much force do you have to exert? That seems like a more logical thing. So I know that the force perpendicular is 35 divided by 0.25 is basically 35 times 4. 35 times 2 is 70, and 70 times 2 is 140. So 140 newtons. So that's what this component is right here, the perpendicular component of that. Maybe I might want to turn it around to make it look right. Make sure I pull. So I know that this component is 140. So what I'm going to do, I'm going to say the cosine. I'll say the cosine of 60 degrees is the adjacent 140 over the hypotenuse, which is my unknown force, F. So I take 140 divided by the cosine of 60. $140 divided by, make sure I'm in the right mode now. I'm in degree mode, that's good. The cosine of 60. I get 280. So this force, F, equals 280 newtons. Another example problem that we can do with torque is the balancing of torques. So you've got two girls on a seesaw. It says, i.e. Carrie Ann and she's 56 kilograms. And Aisha, she's smaller. She's 43 kilograms. Where do I put this pivot such that they balance? Now I know kind of from common sense I'm going to probably put it next to her because to make this thing work. Now this whole principle here works on what's called the balancing of torques. Equilibrium. It means that all forces balance. Meaning that if I add up all the forces in the x direction, they have to equal 0. And if I add up all the forces in the y direction, they also have to equal to 0. This means everything that pulls left equals right. And this means everything up equals down. And it also means, equilibrium means that all the torques balance. Meaning that if you add up all the torques, that's a J, not a tau. They also have to equal 0, which means that all the clockwise torques have to equal all the counterclockwise torques. And a lot of times, sometimes I like to call these negative, and I like to call these positive. It doesn't really matter which one's which, just so long as you understand that they're going in opposite directions. So here we go. This young lady has a mass of 56 times 9.8. So 56 times 9.8. And you get 549. And she has a weight of 43 times 9.8. So 43 times 9.8. 421. I don't know this distance here, but I know that the seesaw, the whole seesaw, is 1.75 meters long. So I know that this distance is 1.75 minus x. For instance, like if this was 1, this would be 0.75. That's what that means, because you just take 1.75 minus the other one, and you can get the other guy right there. So I'm just kind of writing it in math speak. So here's what we got to do. And there is some supporting force right here. We'll call it the force up. What I'm going to do is, this is the pivot. This young lady on this side, Aisha, she is turning this thing clockwise, and then you've got the other young lady, Carrie Ann, she's cranking this thing counterclockwise. These two torques have to equal one another for this to balance. So the torque of Carrie Ann has to equal the torque of Aisha. So it's just the force perpendicular times the distance, force perpendicular times the distance, and you fill in all your numbers. The force perpendicular of Carrie Ann is 549 times her distance. Her distance is x. Carrie Ann is Aisha is 421 times her distance, 1.75 minus x. So here comes algebra. What you're going to do is you're going to distribute this. So you get 421 times 1.75. And you get 737 minus 421x. That equals 549x. So you're going to take 549 and you're going to add to it 421. So 549 plus 421, and you get 970. So now you can figure out what the answer is. You can take 970 divided by 737. It comes out to 1.32 meters. And then we ask ourselves, does that make sense? Where? 1.3. Oh, yeah. No. Well, that doesn't quite make sense. Yeah, now that I think about it, it does make sense. Like if you're gonna do this, yeah, this has been bugging me for a few minutes now. I got an answer of 1.32 meters, and I don't know what I did wrong, and now I think I figured it out, because I know that I should be putting this pivot closer to the heavier girl to make this work. I mean, that's how it works back in kindergarten. So I'm like, I know this number should be less than half of 1.75, which is 0.75. So I know this number's too big, and I think I figured out what I did wrong. Back here, I have to make sure I take 737 divided by 970. So I'm sure that you guys are sitting there watching me do this and saying, "Oh my gosh, he's an idiot." And that's what I have to see. I took it divided by a 737. I should be taking 737 divided by 970, and that makes sense. So 0.76. 0.760. And that makes more sense, that it should be closer. Where should they place the pivot point? 0.76 meters from this girl right here, which is Carrie Ann. Now you may be asking yourself, why didn't I include this force? There is a force right here, but this is not turning if you push on the hinge of a door, that doesn't turn the door. So this up force, we know that this up force is going to equal 549 plus 421, which is 0.47970 newtons. That's how much force is on this actual fulcrum right here, but it doesn't create a moment or a torque around it because you're pushing on the pivot. So that's part one. It deals with torque. What is torque? It's the ability for a force to turn an object. We can figure out what the torque is by pushing at an angle, pushing at a perpendicular, or we can balance torques. We're going to be using this whole idea of equilibrium in section 8.3 again. In equilibrium being, we're going to use all three of these guys to figure out some very complex problems.